For a small body to leave the gravitational pull of the Earth, we must estimate the escape velocity of that body, be it a satellite or be it any object revolving around another astronomical body. So what do? We need to understand something. We are using these two diagrams to illustrate that. If we assume, for instance, that this is the Earth, revolving around the Earth is a satellite, maybe a moon or whatever you may call it. But the satellite moves round the Earth with certain amount of speed or velocity, so to say. If we understand that, it means for it to move around, there is some amount of centripetal force that it experiences as it revolves around the surface of the Earth. We are not talking about leaving the grip of the gravitational pull of the Earth. No, we are concentrating now on finding out the value of the speed or velocity of the satellite while it revolves around the surface of the Earth. It means we need to consider centripetal force and then the force of gravity of the Earth or universe. That means centripetal force Fc is given as mv squared. We are talking about satellites all over R. And that R should have reference with the radius of the Earth. And then the other one is F. The force of gravity is G, me, and then m all over Re squared, which is also the radius of the Earth. So if we have gotten this, we now equate centripetal force to force of gravity, and that is Fc, F subscript C equal to capital F. Now we substitute. By the time we substitute, we have G, me, m all over Re squared, okay, is equal to centripetal force mv x squared all over R. And look at that. Very simple. If we have this, what we need to do is to cancel out. This m will take care of this m. And then we have that m goes against m, good, and then this R will lower this. And finally we now have that all that happens, and we now have the velocity of the satellites is given as square root, okay, gme all over re. So with this formula, we can now calculate the velocity of the satellites. Now we have found this. There is need for us to know the amount of velocity required for this satellite to move away completely from the grip of the gravitational pull of the Earth. And for us to do that, some amount of work needs to be done by the satellites. And if that is the case, we need to redefine some other things, and that becomes work that has to be done is equal to F times distance. That's what we mean by this second diagram. And as we continue to navigate through that, the work done is given as G MEM all over R squared E times, this dot represents times R. So if we have this, when I know that this R, we lower this a bit. And finally we have this. The work done now becomes W is equal to G MEM all over R E, so to say. We have this. That's the work done. That is the work the satellite has to do for it to be able to pull itself away from the grip of the Earth's gravitational pull. Take notes. But there is something interesting about this. As it is doing some amount of work, such work is also equitable to its kinetic energy. So we equate, without wasting time, we equate immediately. W, the work done, is equal to the kinetic energy of the satellite, simply because the satellite is always in motion, and any object in motion, according to simple concept in physics, possesses kinetic energy. So we must take note of that. Very, very important. If we have understood up to this point, then the rest is very simple. What we need to do, we now restate this once again. G, M, E, M all over R, E is equal to 1 all over 2, M, V. This time around we use VE and then squared. VE squared. If that is not clear, I can still restate it once again to make it clearer. Alright? So what we need to do at this point, let me shift a bit. We have our G. The work now is equal to G, M, E, M over R, or squared E dot R, okay? So if we do that, we have this. That's what it means. Okay? So finally we have that, it becomes G, M, E, M all over R on E, okay, is equal to half, I need check, is equal to half M V E squared. Look at this. Look at this. Very simple. So we are looking for escape velocity of the object, be it a satellite or any object, so to say. By the time we make VE the subject, remember that this N, we take care of this N, and then VE, being the escape velocity of the satellite or the object, is now 2G R, okay? Suppose R is equal to R capital. Look at this. We now have G's. Because, hold on, let's check something. 2 comes to this point. Okay, it's not time to reach. And the next step is going to address this. So we are going to have just VE is equal to square root G, 2G, okay, 2G, very good, all over R. Okay? So we are going to look at when R is equal to capital R. Let's see what happens there. Suppose R is equal to capital R. This is very, very interesting. So look at it very well. So with this formula, we can then calculate the escape velocity of the satellites. We can, yes. In my next class, I am going to state another formula similar to this, whereby we're going to substitute 1 or 2 things here, okay, and then capital R will take effect in my next class. I don't want this video to be too long. Thank you for watching. Don't forget to subscribe, give me some thumbs up, share with your friends, network, and students, and then remember to push on. I always like to use the word push on because the finger says push on the bell button for constant notification so that each time content like these are uploaded, you'll be notified. Thank you so much. See you. I am signing out.